Today we're going to look at graphing square root and cube root functions, and technically, yes, you could do this in your calculator, but it's actually a little bit easier to do this by hand, and I'm going to show you a method for number 3 and 4 that makes it pretty easy. So you could put this in your calculator, go to the table, find points, put the points on your graph, but that would actually take you longer than just graphing it by hand. And we need to talk about the domain and range, and the calculator doesn't help you with the domain and range. So you need to know how to look at the graph and figure out the domain and range from the graph. Okay, the first thing I want you to think about for each of these problems is, am I working with a square root or a cube root? So number 1, is number 1 a square root or a cube root? Square root. And a square root function undoes perfect squares. So when we pick x values to plug in, we want to pick perfect squares, like 0, 1, 4, and 9. Okay, 0 is 0 squared, 1 is 1 squared, 4 is 2 squared, and 9 is 3 squared. So we're picking our perfect squares. We're picking our perfect squares because the square root of a perfect square is a whole number. So the square root of 0, if you were to plug these x's into this function, the square root of 0 is 0. The square root of 1, the square root of 4, and the square root of 9. Plot those 4 points, and let's see what this graph looks like. Although you already know, because we did this yesterday, but, so 0, 0, 1, 1, 4, 2, 9, 3. If you remember from yesterday, the square root graph curves up like this in the positive first quadrant and does not continue left of that 0, 0 point. So it starts at 0, 0 and curves up and over. Okay, the domain and range. Remember that domain has to do with the x values. What x values did we put into this graph? 0, 1, 4, 9. What do you see is absent from those x values? Did we plug any negatives in? Why didn't we plug in any negatives? You can't take the square root of a negative number. That's an imaginary number. It's not possible. And that's why this graph doesn't continue over here on the left. You can't do the square root of a negative number. So our x values all have to be greater than or equal to 0. And if you look at the graph, look at that first point on the graph. It's at 0. All of our x values are 0, 1, 2, 3, and bigger. The range. Because we didn't plug in any negatives, because we can't plug in any negatives, what do you notice about the y values? They're all positive. So our range is y is greater than or equal to 0. This is a parent function for a square root graph. For square root graphs, the parent function domain and range is x is greater than or equal to 0 and y is greater than or equal to 0. Next, number 2, a cube root function. Y equals the cube root of x. This time it's the cube root. Can we take the cube root of negative numbers? Yes, if it's an odd index, you can have negatives under the radical. So we want to use the perfect cubes. Remember, the perfect cubes are, let's see, 1, 8, 27. It's 1 cubed, 2 cubed, 3 cubed. But I want negative numbers as well. So negative 8 is a perfect cube. Negative 1, 0, 1, and 8. And the biggest question I get in this section is, how do you know whether you should use 0, 1, 4, 9 or negative 8, negative 1, 0, 1, 8? You want to look at what kind of root you're working with. Are you working with a square root like in number 1, or are you working with a cube root? If it's cube root, use the negative 8, negative 1, 0, 1, 8. So the cube root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is negative 8. What is the cube root of negative 1? Negative 1. The cube root of 0 is the cube root of 1 and the cube root of 8. plot those 5 points. You are going to like the domain and range for cube root functions. So domain, x values. Did we put negatives into our function? Did we put positives into our function? So the domain is everything, which in math we call all real numbers. Remember that a capital R with a double stem is a symbol that represents the word real numbers. So all, the word all, and then a capital R with a double stem means the phrase all real numbers. Anyone want to take a guess what the range is going to be? All real numbers. Okay, now let's look at what happens when we shift these graphs horizontally and vertically. So number 3, the first thing that you need to think about is this a square root or a cube root function? Cube root. And because it's cube root, we are going to use -8, -1, 0, 1, and 8. Okay. This one's actually pretty easy because there's no stretch. But I want you to think about this graph just up to the x. So circle this graph just to the x. And basically, for right now, pretend that the +1 and the -2 don't exist. We are going to plot these points as temporary points. So underneath this table, I'm going to write temporary. Okay? Because there's no stretch, these points are going to be same as the parent function. Y equals the cube root of x. So -2, -1, 0, 1, 2. When we plot these 5 points, I want you to either use a different color pen or a different symbol. I'm going to use a little X because in my mind on a graph, if a point has an X through it, that means it's like not actually a point. It's just kind of there for reference. So my temporary points, I'm going to use a little X. So here's a temporary point, temporary, 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 and temporary. Once I have my temporary points on the graph, don't connect them because we're not actually graphing these temporary points. We're just using them as a reference. Because this graph has something else in the equation. What does the +1 do to this graph? It will move this whole graph left 1. What will the -2 do to this graph? It will move the whole graph down 2. So these temporary points need to be moved left 1 and down 2. So take each point left 1, down 2, and put in the actual point. And then connect those. Whoa. The really nice thing about cube root graphs is the domain and range. Domain, all real numbers. Range, all real numbers. In number 4, how are we going to stretch the temporary points? That's actually pretty hard to do, just to like last minute stretch the points. So instead, do you see what we did in number 3 where we circled everything up to the x? I want you to circle everything up to the x. End it right after that x. So we are actually going to make a table of values for y equals 2 times the square root of x. The stretch will be taken into account in our table of temporary values. Then all we're going to have to do later is move this left or right, up or down based on the rest of that equation. Because this is a square root I'm going to use 0, 1, 4, 9, my perfect squares including 0. So, plug 0 in. What is the square root of 0? And what's 0 times 2? 0. Now, plug 1 in. What's the square root of 1? And then 1 times 2 is 2. Plug in 4. The square root of 4, 2. 2 times the 2 is 4. And now you're 9. The square root of 9, 3. Then multiply that 3 times the 2, 6. So our temporary points already have the stretch incorporated into them. So we don't have to worry about the stretch anymore. So plot these temporary points. We've got 0, 0, 1, 2, 4, 4, and 9, 6. Don't connect your temporary points, just get them on there. Now we can think about how we need to move those temporary points. So in this equation, what does the minus 1, what is that going to do to our graph? Minus 1 underneath the radical means horizontal movement, and horizontal movement is backwards. So minus 1 means we're going to move each point right 1. The plus 3 is not under the radical, so it's going to move the graph up or down. Up or down is normal, so that's going to move the graph up 3. So move each point right 1 and up 3. And remember that point on the left, your graph does not extend beyond that point on the left. Okay, the domain and range. Because the graph moves side to side and up and down, our domain and range is going to move side to side and up and down. If you take a look at this point, what is the x value of this first actual point? 1. Just take that point and drop it down to the x-axis. It has an x value of 1. All of our x values are 1 or larger. So our domain is x is greater than or equal to 1. This point has an x value of 1. All of these other x values are larger than 1. So our domain is x is greater than or equal to 1. You can also look at how the graph moved to determine your domain and range. The graph moved right 1, so that domain has to move right 1. The domain is affected by the right or left movement. So you may want to write that above your domain. The domain will be affected by your right or left movement. So if we had moved this graph left 4, our domain would be x is greater than or equal to -4. Your range is affected by up or down movement. So who wants to be brave and guess what the range is going to be? Y is greater than or equal to 3, because we moved the graph up 3. And if you look at the point, this first point has a y value of 3. All of these other y values are bigger than 3, so 3 and above.